Baby.
Good morning. Thank you, Andrew. I was muted. So I was hoping that you would have questions on any subject matter that has to do with exam 2A, 2B, which is closing on Friday. And we could take some minutes of the class to do that. Then after that, we could, maybe we can do that 20 minutes. This afternoon, I'll be available from 1:30 p.m. to 4:30 p.m. or until the last person leaves the room. Which, yesterday was around 3:45, 4 p.m. So today I'll be there from 1:30 to 4:30. Let me send you the invite now while we're at it. Let's see. Today at 1:30. So copy the URL. And that's really pretty, whoever has birds. That's really pleasant. Thank you.
Oh, the chicken next door.
Oh, that's cute. That is so awesome. That just like, it makes it like I don't know, like springtime. It's just very lively. Okay, so all you have to do is, this is the meeting room, and I'm sending it to you right now.
Yeah.
And then you should get it. That way you can have access this afternoon to asking more extensively about exam 2A, 2B, which is closing this Friday, and anything about chapters 3 and 4. So I hope if you receive it and you can send me a little chat saying, yes, I got that message, then I know that things are at least working. And so now we can move on to Pearson and to your questions. Do you have any so far? Any questions in where you are progress-wise? If you don't, I'll just do a little bit of lecturing.
I do have a question, Alan.
Yes.
Good morning.
Nice to see you as well.
Nice to see you too. It's on lab 6, question number 6.
Mhm.
And I have found A and B. I have a problem for the formula for the C part.
Okay. So that question has to do with remember what that question was about?
Yes. Give me a second. So the manufacturer of game controller is concerned that its controller may be difficult for left-handed users. That question.
Got it. Okay. So can you see the board work right now?
Yes.
Cool. So in that question, manufacturer is making controllers for gamers. And the problem seems to be that left-handed people have more trouble using it than right-handed people. So what's happening there is what's going to be random is that you're picking a group of 8 people in my problem in a population where 13% of the people are left-handed. And so the way to think about this problem is that as you're selecting gamers to test the controller in, a gamer either is a righty or a lefty. Okay, so a gamer is either a left-handed gamer or a right-handed gamer. If 13% of gamers are left-handed, as is the case per my question here, then it has to be the case that by the rule of complements, 87% are right-handed. So that's what we're going to call P and Q. So this is what we're going to call the probability P of a success. And then this is what we're going to call Q, the probability of non-success. And then what we're going to be counting we're going to be counting X. X is going to be our counting variable. And X is going to count something. It's going to either count the number of gamers sampled until the first lefty.
This is not right.
Until the first left-handed person. That's what a geometric count counts. Okay. Alternatively, X can be something else. It could be the number of lefties in the group of 8. sampled. And the group of 8 is what we would call the number of trials. In that case, we call this a binomial model, a binomial count, as opposed to, in the first case, that's called a geometric count. So depending on the nature of the question, you're going to either use the geometric calculator or you're going to use the binomial calculator. So let's get to the problem, your version. Okay. I'm going to put this aside for a moment and let's go back to Pearson. And look at the assignments. Lab 6, question 6.
Yes.
And it's opening, so it takes a second or two. I don't know why my connection is a little slower today. So again, it's about a manufacturer of game controllers. The controllers seem to be hard to use but for left-handed users. 13% in my case of the population of interest is left-handed. And I'm sampling 5 customers from the population of customers to test the controller. And I want to know what the probability is that X is equal to 3. And in this case, X is the first lefty, is the third person chosen. Okay. So what I have to do to solve this problem is I have to open StatCrunch and open the open StatCrunch, and in particular, we're going to open the geometric calculator to work on it. Okay, so here's StatCrunch. All the calculators we use in chapter 6 and in chapter 7 are under the stat button and under calculators, stat calculators. So calculators here refers to the different models of probability, not to an adding machine. And we're going to go and look for the geometric calculators. And we're looking at how many trials have to take place in order for me to find a first left-handed user. So the correct calculator comes from that sequence of commands: stat, calculators, geometric, number of trials. And that's what it looks like when you open it. The first thing to select is the probability that we're going to call the probability of a success, the probability in this case of finding a left-handed user, which is 13%. So this 13% comes from, in my question, you may remember that about 13% of the population is left-handed. So that's where the 0.13 comes from. And then I want to know the chance that as I am selecting 5 people, the third person is the first lefty I select. So I change the sign of the probability calculation to an equal sign because I want to know the chances that the third person is the first left-handed person. And then the answer is automatically computed to that, 0.0984. Okay, so then I just go back to the homework and I put here 0.0984. And that's it, magically. Then in part B of this question asks, there are some lefties among 5 people. Some lefties among the group of 5. So notice how this question is not asking you to count when do you see the first lefty, but rather how many lefties are there in the group of 5. So this is a binomial count probability, not a geometric. Because as we said earlier, the distinction between geometric counts and binomial counts is that the counting variable is called geometric when you're looking to see the first lefty in your sampling scheme. If you're counting the total number of lefties in a group of 8 in this case, or in a group of 5, or in a group of n, then that's a binomial count. So that's the difference between a binomial and a geometric model. So going back to the question, some lefties among the 5 people. How do I write some lefties in the group of 5? And the answer is some means more than none. That's how I write the probability of some. Greater than 0 means some. Okay, so I'm going to go now to StatCrunch again. And this time I'm going to, instead of opening another geometric, I'm going to open the binomial calculator. And the way you do that is stat calculator's binomial. Click on that. You can see that the 2 calculators look very different. The geometric looks very different from the binomial. In the binomial, I get a place for the number of total tries. In my case, that's a 5. The probability of a left-handed person is 13. And then I change the probability of x to being greater than 0. Because that's how I write some, greater than 0. And so the answer is 0.5016. So then I go back to the question and I put here 0.5016. Part C asks, what is the chance that the first lefty is the second or third person? So I need to calculate the probability in a geometric model that x is 2 or 3. And I know it's a geometric model because it's about finding the first lefty in the group. So that's what tells me it's geometric. And then second or third means that I want the probability for x being equal to 2 or 3. So to do that, I change the calculator, the geometric calculator, from the standard mode. The standard mode is what allows you to calculate the probability of one thing. If you change it to the between mode calculator, the between mode allows you to calculate more than one outcome at a time. So 2 or 3 are these 2 red bars here, and you can use the between calculator to just have the software do the whole math for you. That way you don't have to individually do the probability that x is 2 or that x is 3. And that's 0.2115.
And what's up?
So far, so good?
Yes, thanks.
There are exactly 3 lefties in the group. So exactly 3 is x equals 3. And because this is not about the first lefty, but about the group, it's a binomial count. So I again go to the binomial calculator and do x is exactly 3. And that is 0.0166. So then part E asks, there are at least 3 lefties in the group. At least 3. That means 3 or more. So all I have to do is, in the binomial calculator, I have to change this equal sign to a greater than or equals, and that converts it to at least 3. So that's at least 3. And then the last part says there are no more than 3 in the group. So it's binomial, and no more than 3 translates into changing the computation, the earlier computation, to no more than 3. No more than 3 means less than or equals to 3. Was that, did I do okay? Did I go too fast? I could repeat any part for anyone, any component.
Can you repeat from E?
Sure.
Thank you.
So D says there are exactly 3 in the group. E says there are at least 3 in the group. And F says there are no more than 3 in the group. So the key is the language that precedes the number 3. Exactly 3 means equals 3. At least 3 and no more than 3 refer to at 3 or more versus 3 or less. And so when you use the calculator, you need to just change the algebra part here to one of these 5. This means equals. This means greater than. This means less than. This means at least. So at least would be part D, or E, sorry, part E. And then at most means less than or equals, and that would be part F. So anytime you see the language at least, then use the greater than or equals. When you see at most, use the language of less than or equals. When you see exactly or is, then that's equals. If you see some means more than none. Okay. If you see more than or less than, then you got to strictly use the greater than or the less than sign. In this portion here of the calculator. And then sometimes you're going to have from one number to another. So then you use the calculator in between mode as opposed to standard mode. And then you have a number, then a less than or equals to, then X, then another less than or equals to, and then you'll have another number. You'll have A here and B here. Okay, so that's when you change from standard to between. You see how you can control where to start counting from like 1 to 3, for example. And that counts the 3 probabilities and adds them all for you.
Okay, thank you.
You're welcome. I'll leave that there for a second in case you guys want to take a picture of what a standard looks like versus what a between calculator and some of the language that you have to take into consideration when you're using these probabilities.
Quick question about B on this problem.
Yes.
Where there are some lefties among the 5 people, I actually used the geometric calculator and I put X is less than or equal to 5 and I actually got the same answer. Is that like, because you used the binomial and I wasn't sure like what the difference was.
The difference is that, again, the geometric is only calculating when do you see the first lefty. So when you see the first lefty, it could be in the 5th place, or it could be in the 4th, or it could be in the 3rd, or it could be on the 2nd, or it could be on the 1st try.
Okay.
And so when you do the math for that in the geometric world, that's the same as the binomial, where you see more than 0 lefties in the group of 5.
Mm-hmm.
So it's just a different way of telling the same story.
Okay.
But a geometric calculator is easiest to remember as measuring the chances of you seeing something happen for the very first time.
Mm-hmm.
And a binomial is counting how many total times you see a lefty in a group of 5 or in a group of n. So there will be stories, geometric versions of probabilities of outcomes that coincide with binomial stories. When you say you want some lefties, that means more than 0. So that means 1 or 2 or 3 or 4 or 5. So if you see a lefty in any of those places, then you'll get the same answer. Any other question in that lab or any lab? We could do a little bit more before I want to introduce the normal model to you, chapter 7.
Can we do, what was it? Question 3 on quiz 6?
Absolutely.
Thank you.
So I'm going to go back to the assignments and open quiz 6. Okay. So do you remember what the question was in your version of the quiz? Adam?
It's it is estimated that 20% of luxury cars manufactured in 2012 are silver. A car dealership typically sells 20 luxury cars per month.
So
What is
in
the
mine,
probability
number 4.
Okay.
Okay. So we have this question and it's a multiple choice question. Okay, and I'm going to open a board for it. So we'll call this quiz6 luxury car question. And the answer is one of these four. So let's see what the problem reads. It says, it is estimated that 20% of luxury cars are silver in color. And so here I have a luxury car. And it is either thought of as a silver car or not silver. And therefore, if this branch is 20% chance, then this branch has to be 80% chance. And what I just developed here is what we called a Bernoulli trial. That's what every decision about every car will be in this problem. In addition to that, we are told that there's a total of 20 of these cars in a month, typically. So the process of whether the luxury car color is silver or not silver repeats a total of 20 times in a month. And so then the question is, what am I counting? What is X? X is the number of luxury car color silver. And the answer is, it can be anywhere from 0 to 20. Out of 20. And this is what tells me that this is a binomial calculation. Because it's how many cars out of the 20 are silver. And in particular, I want the probability that X is exactly 8. Of course, out of 20. So what I'm going to do to solve this problem is I'm going to go to StatCrunch and look for the calculator called Binomial. And I'm going to set n to 20, p to 0.2, and x to 8. And then I'm going to compute and get the answer. And I think it's a small probability. I think it's something like 0.0222 or
Yeah,
something.
I just did. It was 0.222.
Cool.
Right,
So,
thanks for the help. I just didn't know what model to use.
right. So because we're counting silver cars out of 20, then it's a binomial. If the question was, what is the chance that we will see the first silver car in the 7th car observed, then it's a geometric.
All right.
Another key, another insight is when the problem involves a binomial, you need to know, you need to be given information about P, the probability of success of what a success is in your context. And obviously then Q, which is just the complement of P. But also you need to be given the number of total trials. Whereas when it's a geometric question, you'll only be given P and Q. You don't need anything else.
All right.
And the question will be about the first time you see silver. Then that's geometric.
Okay. And do you think before we go on to chapter 7, you can do a quick example of, I don't know how to say it, but the Poisson
Poisson?
model? I don't think we've gone
Yeah,
over
sure.
that yet.
Oh, then let's do that.
All right, thank you.
Yeah, for sure. So just to remember, we had a family of models called counting models. And we said that there were 3 models of counting, where X is the counting variable. So a counting model is about a variable that helps you determine one of 3 things. It could help you determine the first instance you observe something of interest. That's what we call a geometric model. The total number of observations that occur observations of interest that occur in a finite number of trials that we call n. And that's the binomial model. I think that's where we left off on Thursday, right? So then the third model is when you count the total number of observations of interest that occur in an unknown number of trials. So in this case, you don't know n. However, you know the rate of success. So in a Poisson model, n is not known. The only thing you know is a rate of success. And that rate of success is like a number per unit of time or number per unit of space. And that's what we call a Poisson count. A fish count, basically. Because it's almost like, imagine you're at an aquarium and you're watching at an enormous fish tank. And the only fish you like in the whole fish tank are, say, I don't know, goldfish. And this tank has everything from sharks to little tiny things. But you only are caring about goldfish. So either a fish is a goldfish or it isn't a goldfish. and you're trying to count how many goldfish there are in this pool of water. And so, you know, it's kind of like the Monterey Bay Aquarium. It's an enormous fish tank. So it's really hard to know how many total fish there are in this tank. And it's really hard to find out how many goldfish there are. But you know that if you stare at the tank, for every minute that you stare at the tank, you're going to see 3 different goldfish per minute. So that's what we would call the rate of success. That if you stare at the tank for a minute, you expect to see 3 goldfish. But you're just not going to see 3 every minute. Some minutes you'll see 0, 1, 2, 3, 4, 5, 6. Every minute varies from minute to minute. And but the average is going to be 3 per minute. So if you stare at the tank for 5 minutes, you're going to see about 15 goldfish, not just 3, because 3 times 5 is 15. So that's what we mean by a rate of success. And this rate is scalable. Scalable means that if you can think of 1 minute, you can think of 10, you can think of 5 and whatnot. So let's look at a problem from this quiz. And I'm looking at the problem in this quiz where you are looking at controlling the quality of SIM chips that go into cell phones. Okay, so I'm going to put that over here. So this is a quiz 6 question about quality of SIM chips in cell phones. Okay. And the problem reads, for quality control purposes, a company that manufactures SIM chips for cell smartphones routinely takes samples from its production process. Since it is important that these chips are nearly fault-free, one inspection check involves using microscopic equipment to count the number of imperfections on the chip. Suppose that the average number of imperfections per 1,000 SIM chips is 3. Okay, so this is the average number of imperfections every 1,000 chips. So if we were talking about 10,000 chips, we should find 30 imperfections. Does that kind of make sense? That since the average is 3 per 1,000, in a group of 10,000 chips, it would be 30, not 3. That's what we mean by scalable. So that's what we mean by the rate of success in this case. And then comes the question. The question is, what is the probability that a sample of this size, the sample being of 1,000 chips, has no more than 2 imperfections? No more than 2 imperfections means what? It means that we're interested in the probability that X is less than or equals to 2 when the rate of imperfection is 3 per 1,000. And so that's what makes this a Poisson, that we don't know how many times I'm going to be checking batches of 1,000 chips. So then I will go and click on Stat, and on Calculators, and on Poisson, and I will set the mean to 3 and calculate the probability for X being less than or equals to 2. And then compute. And the answer will be one of these four. So let's go look at that in. Okay. So I go stat, calculators, and just like you open a binomial or a geometric calculator, you open a Poisson. And then you set the average rate to 3 defective chips per 1,000. And you want to know the probability that you observe no more than 2 defects. And it's 0.4231, 0.4232. So then when you get to the quiz, it's this one. So that's an example of a Poisson. Notice that in a Poisson problem, in the whole language, there's never any percentage given. So P and Q are not given. So the fact that you don't have a probability of success and a probability of failure, a P or a Q, tells you it cannot be a geometric and it cannot be a binomial. So it has to be a Poisson, because those are the only 3 counting models we have here. Because we're counting how many bad chips in a batch of 1,000 when the usual is 3 bad chips per 1,000.
Can you go back to the whiteboard real quick so I can take a picture of it?
Oh, show. And then I'll put a stamp on it there.
Thank you.
Mm-hmm. Let's look at other problems that might be of interest here. So this one's a little tricky, but it's super easy once you get the trick. Suppose you work as a customer service rep for a company. And the way that your performance is measured is by how many phone calls you get from credit union members that need your help about something. And the number of calls has a uniform distribution. So a uniform distribution is when everything has the same probability of occurring. In this case, you get anywhere between 0 and 6 calls per minute. So this is called a discrete uniform model. And when you see the term uniform, it means that all the probabilities are equally likely. Okay, so what that means is that the probability that you see no calls coming in is the same as the probability that you see 1 call coming in is equal to the probability that you see 2 calls coming in, or any other value. Does anybody know what that probability is?
1/6, or like 1 out of 6.
Okay, and where did you get 1 out of 6?
Because you said the probability of getting like 1, 2, or 3 calls is the same or equal.
So you can get 0 calls, or 1, or 2, or 3, or 4, or 5, or 6. I just put 7 check marks there. What that means is that, and that's what's tricky about this problem, that this is actually 1 out of 7. Because there are 7 possibilities. Because 0 is another possibility. So everything has a 1 in 7 chance of happening. So then when the question asks, and that's the tricky part of the question, what is the probability that at least 3 calls are received per hour? What's the probability that x is greater than or equals to 3? Then that equals the probability that it's either 3 or 4 or 5 or 6. And notice how many different values that is. That's 4 possibilities. And each one of them has a 1/7 chance of happening. So this is 4 and 7 would be the answer. Does that make sense?
Yeah.
So be careful with these tricky problems that look easy, look super simple, but there's usually like a little trick about them. So it's not 4 and 6, it's 4 and 7. Because you have to count the 0 as a possibility. 0, 1, 2, 3, 4, 5, and 6. So it ends up being 7 total possibilities. And then you still have to remember the possibility that you have a custom model. The custom model was the first one we covered last week. And sometimes the custom model requires that you look at a contingency table. So this is just like several problems in quiz 5 and in lab 5. This problem about using 2 kinds of brokers. So keep track of custom models of probability. They can be contingency tables, like in chapter 5. So you have investors. So here you have the world of investors, all investors. So I'm going to put here the probability of 1. Which just means all investors. And then 60% of investors use a full service broker. So if I color this in green, if I color 60% of that, those are full service broker investors. That means that there are people who don't use full service brokers and they amount to the other 40% of the story. That's the white part. Then 30% trade stocks online. So there are some investors called online investors, and then there are other investors which are not online. And so I can separate the online and the non-online into a group of 30 and 70. So this is 30% are online, which means that 70% are not online. And then it says, so I use the red lines to take the 30% who trade stocks online. And then 24% do both. So this 24% does both. That means that this block here is a little less than a quarter of the whole thing. Now, if that's 24%, I hope you can see that this has to be 36%. Do you see that? Because the two parts together have to add up to this 60% here in green. Okay, because this is, that 60% is the sum of these two parts here. Okay, so these two things here have to equal that thing there. And that gives you the solution to the other two parts. This has to be 6% because the 24 and the 6 have to add up to 30. And this has to be 34% because otherwise the 36 and the 34 would not add up to 70%. And the 6 plus the 34 gives you the 40% too. So it all matches internally. So when you are then asked what is the probability that an investor uses a full service broker or online, then you can apply, then you make sure you count everything that has an or. Or means that you're going to look for anybody who is a full service broker or an online broker. So the full service brokers, are these and these. And the online brokers are these and these. And so the answer to the question of what this probability equals is 0.06 plus 0.24 plus 0.36, and that is 0.66. So the answer to the question then becomes 0.66 or 66%, whichever one fits in your model. Okay. Ah, there it is. This one is about two magazines, Food and Wine and Wine Spectator, and it's the same structure as the one that we just did. But instead of having investing online and investing full service, you have people who read Food and Wine magazine or not read, people who read Wine Spectator or don't read Wine Spectator. So this is another model, and it is called a, this model here is what we call a custom model again. And the question is, what is the standard deviation? So we do that in the same way we did custom models last week. We put the information in StatCrunch. So that's the model. There are 5 possible outcomes, and we know all 5 probabilities. So the way we use the custom model is stat calculators custom. The values are called the number of ordered units, and the weights are called the probabilities. And when you hit compute, you get the mean and the standard deviation. So just like we did in last week when we were studying the custom model, I just thought it'd be good to go back and review a little bit of things that are different than the standard deviation is 6.6, different than the counting models that we've been playing with more recently. This is another custom model. I know it's custom because it tells you each probability for each outcome. So it tells you about a computer that needs no repairs, or 1 repair, or 2 repairs, or 3 repairs, and that none requires more than 3 repairs in a year. And then you want to find the average number of repairs. And so the way you do that is you mount this question, you mount these probabilities into StatCrunch. Because you could have the number of repairs can be 0, 1, 2, or 3. And then the probabilities of repairs are 86, 9, 4, and 1%. So once you have the model, you just let the custom calculator know where the values and the probabilities are. And the expected value is right there. The average is 0.2, give or take 0.54. And then this is another Poisson model. It even tells you that that's what it is. And then it wants to know what is the probability that there are fewer than 3 claims on any given day. When the claim is about the number of lost pieces of luggage in an airport tend to average 9 a day, what is the chance that you will see fewer than 3 claims per day? Okay. I'm going to go back to the whiteboard and go back to the page that we were using earlier for the Poisson models. Okay. And I'm going to put over here this other question. So in this case, the mean is 9, and x is fewer than 3 in a Poisson calculator. So let's see how that works. We would go into StatCrunch and go Stat Calculators Poisson. Set the mean to 9 pieces of luggage is lost per day. And what is the chance that you see fewer than 3? And it is a very, very small probability. There's less than 1% chance. So then what we do is we take that number and we locate it in the quiz. Okay. The secret to chapter 6 then is to ensure that you get the right model. If you get the right model, it's going to be really easy to then figure out the question. And because the calculator usage is fairly transparent, fairly easy. So look for the model in the question. If the question gives you a ton of details, it's probably a custom model. A custom model. A custom model. A binomial. A binomial. A uniform. A custom. A Poisson. The reason I didn't ask geometric questions in the quiz is because we did a ton of geometrics in the lab. So the lab and the quiz in this chapter supplement themselves very well. And if we look at exam 3, we know that there are 4 questions in exam 3 that have to do with this chapter. Here's a question about chip manufacturer rejecting 7% of chips. The 4th is the first bad one, so you know that that's a geometric calculation. They find a bad one within the first 7. That's geometric. The first bad chip is the 3rd one. That's a geometric. The first bad chip is la la la. So this whole question 6 is all geometric probabilities in your exam 3. So once you know that P is 0.07, you're then calculating the probability that X is 4 in a geometric model. Here you're looking for a bad one within the first 7. This says the probability that the first bad one is the third one. And one of the first 6. So problem 6 in your exam 3 is just all geometric calculators. Problem 7 is about expectations. So this is very similar to the Archer question in the lab. How many lefties do you expect when you're doing a binomial count? In this case, you multiply n times p. In my case, you have 5 customers. You have 5 customers in my case. So that's 5 times the probability of finding a lefty, which is 15% in my case. Your numbers may vary. The standard deviation of a binomial is the square root of n times p times q. Where q is the complement probability to p. 0.15 is the percentage of lefties, so 0.85 is the percentage of righties. And then if you keep picking people until you find a lefty, that's not going to be a binomial anymore. That's going to be an expectation of a geometric. So these calculations of binomial and geometric, these formulas for expectations and deviations can be found in your notes for chapter 6. It's actually found in the notes on chapter 6. And then the last 4 problems are going to be all problems from chapter 7, so I'm not going to go into reviewing that in your exam yet. Okay, so as you're working through exam 3, which is due by May 1st, just remember that a good strategy to work on these is to identify what model and what calculation to do. And the models are any one of the models covered in chapters 5, 6, and 7 will have expectations and deviations that are slightly different. And anytime you see about the first bad chip or the first time something happens, your model to use is the geometric. When you're using total number of successes out of n tries, binomial. When you're using total number of successes and they just give you like some they don't give you P or Q or the total number of tries, then it's a Poisson. If they give you a lot of details, it's probably a custom model. And if they give you 2 or more custom models, you can compound them and build a compound out of them. And then the 9 rules of probability are the first 3 questions, are what the first 3 questions are about.
Should have had a massage. Basically that.
Okay, so that's we'll talk more about exam 3 after this week, you know. And in the meantime, I think I already sent you the invite. Who got the invite for the 1:30 to 4:30? Naveed, did you see your inbox just to
I
make sure?
did. I got it. Yeah. And I get a question. Do we have to schedule a meeting, or we can just come up as we do here?
Right, you come in, you in and out privilege, my friend.
Okay,
You can
awesome.
come in and leave. If you want to come in at 2 and leave at 2:15 because you have to do other things, I totally get it. It's kind of like the lab hour. Those 3 hours are more open-ended than this. This was more structured to try to finish chapter 6 before we hit on to chapter 7, but you're definitely welcome to any of those invite hours.
Cool. Thank you very much.
My pleasure. Peace out, guys. I gotta
Awesome.
get going to the
Take
next
care.
lecture.